Welcome everybody to the now last nuanced tech talk of the year, which is ironically signified by large amounts of precipitates in the form of snow outside. So I hope you're all warm and safe. So today I'm very excited to introduce our latest focus ion beam instrumentation to you, the Thermo Fisher Hydra Plasma FIB-SEM, which exists next to, in addition to the Helios Nanolab that we currently have in our EPIC focus ion beam facility. So on the right-hand side, really right off the bat, I would just like to highlight some broad picture capabilities to you to get you hopefully excited and see where this instrumentation might fit in for you and your research. So perhaps the largest hallmark of a plasma focus ion beam is that you can site-specifically remove large volumes of material ranging from hard to soft materials at very large length scales, typically up to the sub-millimeter range. So an example of that is shown here on the left hand side, where we have a cross section of an alloy. So typically we would mill a cross section or a surface. And then the depth of this cross section over here is about 300 micrometers. And we've achieved this cut in about 5 minutes. So to give you an idea of the high throughput volume milling that you can perform with this instrumentation. So we have multiple ion sources present as well. So you can mix and match chemistries of the ion beam with which you remove material to the chemistry of your material as well. But also you can achieve with the ion beam resolution up to the nanometer scale. So that can be beneficial if, for example, you want to do some sample preparation. And in this case, we also have, besides hardware like the ion beam, we have software present that assists you with automated sample preparation across those length scales, like I said, down to the nanometer scale, for which, for example, you can make some very small TEM sections that you can then remove and then analyze in the TEM. Sometimes two-dimensional information is not sufficient, so then we also can do a 3D analysis of materials. So on the right-hand side, we can do imaging of volumes, again, up to the hundreds of microns range for imaging purposes. So we use different detectors for various signals in this instrumentation to recreate a 3D volume for imaging purposes. But additionally, on this instrumentation, we have analytical detectors. We have an energy dispersive spectrometer and for analyzing chemical properties of your materials. And then we have an electron backscatter, the diffractometer present as well, so with which you can analyze crystallographic information, and even in a multimodal fashion, so you can acquire EDS signal with EBSD together in 3 dimensions to, for example, perform this correlative imaging where you can know the chemistry and the mineralogy of your sample. Last but not least, we have a cryo stage present on this instrument, so we can do all of this analysis. Basically, these images are pretty much like material science based, but we can cool down samples to about -90 Celsius. So we could potentially analyze biological materials in their native state, and so then perform these characterization techniques on more beam sensitive materials or materials that need to exist in their native hydrated environment. So I will spend the last part of my talk on that. So jumping back, so I mentioned the plasma focus ion beam. Some of you may not know what a plasma is. So really, basically, a plasma is also signified as the fourth state of matter. So besides your conventional gas, liquid, and solid material classes, that occurs in natural environments. For example, in space, we have like black holes that have plasma. There's comet tails that have plasma in it. but we can also induce a plasma in the lab. So what happens in a plasma focused ion beam? Basically, we can have a gas that's let into this dielectric chamber. And once we apply a magnetic field through the antenna coils over here, you basically get a magnetic induction field, and you get a soup of negatively charged electrons and positively charged ions. And then you can extract the positively charged ions via an extraction electrode. So plasma is one part of the naming convention. What is a FIB-SEM? I elucidated in another tech talk previously. So if you're interested, please scan the QR code, and then you will get linked to that YouTube video. But briefly, so in a FIB-SEM, we have an electron gun, so as conventional in the scanning electron microscope, but we also have an ion column present. And for the Thermo Fisher instruments, this angle between these beams is about 52. It's 52 degrees. And so with the ion beam in the conventional setting, like the Helios Nanolab that I just showed you, we have gallium ions that can get emitted site-specifically, and you can remove material, so that's called milling or sputtering. And then with the electron gun, you can basically induce a variety of signals that you can then detect with a detector onto your computer and basically generate data that way. There is also frequently a micromanipulator present there. So if you, for example, create a very small section of your material, you can lift that out with a micromanipulator, and then, for example, move it to the TEM if you thin it down appropriately to look at your material in the TEM. And then we have a variety of gas injection systems that can be present here. So with which you can assist deposition of materials. So on the Hydra, we have tungsten, platinum, and carbon that we can deposit on a region to protect from cutting it with the ion beam. Or you can have some gases, like etching gases, with which you can site-specifically remove these materials in a faster fashion. Okay, so why would you want to use plasma in a FIB-SEM is the next question. So in the Hydra, we have, as I mentioned, we have multiple ion sources. So we can have xenon ions that can be emitted from the ion column, oxygen, nitrogen, or argon. And basically each will deliver a different outcome if you're, for example, making a cross-section of a material. Now in the Hydra, we can switch between species in less than 10 minutes. So for example, you could do a coarse cut with xenon and then polish with an argon in a relatively straightforward fashion. So this really gives you like the flexibility in sample preparation and characterization, so to match basically the ion to the chemistry of your sample. But as I mentioned previously, one of the probably key hallmarks of the PFIB is that you have these high ion beam currents available, with which you can site-specifically remove very large amount of material. So to give you a feel for this and to compare, and I believe that was actually already a question that I received yesterday, how would removing material on a gallium FIB system look like compared to the Hydra? So to give you some insights into that, on the left-hand side here, this is a milling of a silicon sample at the highest ion beam current available. 30 kV is usually the accelerating voltage that's used for most ion beam conditions. It's the highest resolution beam that you can get. So in 1 hour, we can remove approximately a volume of 40 by 40 by 40 micrometer. In the Hydra with the xenon source, where we can use an ion beam current up to 2.5 microamps, in 1 hour we can remove about 50 times the volume that we can do in the Helios Nanolab. some other benefits of a PFAB over conventional gallium beam FIB-SEM. You can create less surface damage. For example, this is a paper where they prepare a TEM cross section. So basically, you with a micro manipulator, you can lift out a small volume. You can thin that down to electron transparency, transfer it over to the TEM, and then you can measure the surface damage on a silicon sample. So silicon, the atomic structure can get disrupted by impingement on gallium ions. So the yellow lines here indicate an amorphous silicon layer in this sample, and you can see at 30 kV the xenon gives about a 40% reduction in that surface damage layer. And even though at lower accelerating voltage the difference is smaller, you can still see a benefit as to why you would prepare a sample here with xenon. Then another issue that could arise with a gallium FIB-SEM is with specific classes of materials, like, for example, aluminum over here. This is atom probe data. So basically, every dot here will represent like an atom. We have an aluminum scandate alloy grain structure here that's adjacent to an aluminum structure. And you can see in black are basically the gallium atoms that are segregated to the grain boundaries. When you prepare these samples with gallium, obviously you will get pollution of gallium near your grain boundaries. So if you want to investigate the native structure, that gallium beam would not be preferred for these type of materials. Then another disadvantage of using gallium FIB-SEM could arise from if you're trying to prepare or mill gallium-based materials like gallium arsenide. So in this case, you would preferentially sputter remove the arsenic ions from the crystal structure, and you will get this artifact that is called like a droplet formation of gallium that segregates in this way. So I've shown you some comparison of xenon versus gallium. So let's throw another ion in the mix. So we have argon in addition here as well. And so what we're looking at on the left-hand side is a plot of the ion range of these species in silicon versus the accelerating voltage. So over here we have a 30 kV a beam of argon. You can see that it penetrates deeper into the sample versus xenon that actually penetrates at more shallower depths. But that's not the full story, the penetration depth. If you look at 30 kV, again, and we compare argon to gallium to xenon, these are simulations that are done. You can actually see that at the top here is the amount of vacancies that is measured in that penetration volume. You can see that xenon actually creates much more vacancies. And this is basically a measure of milling rate. So xenon at 30 kV will preferentially mill larger volumes as compared to gallium argon. And even though gallium will, for example, penetrate deeper into the material than xenon at 30 kV. Now at the lower kV range, then basically it's the opposite trend. So that trend is reversed. And so, for example, argon could be used to really do a final like cleaning at low or polish at low kV. Some other comparison of ions that I did here. This is actually like a biological sample that was generously provided to me by my colleague Rainer Blair. So these are tumor cells that are embedded in an epoxy on top of a silicon wafer, and on a microscopic, it's about like a microscopic perspective, you can largely see the difference between milling the sample with xenon versus oxygen, which gives this very smooth kind of cut. And if we then dive into the cross section and image the cross section, then you can see that the xenon here creates more like artifacts in the cut. You can see these streaks are so-called curtaining artifacts. whereas the oxygen really provides that nice smooth cut for these type of materials. And this is an example from the literature. On the left-hand side here in this image, this is a gallium beam cut for where, again, cells are imaged and the ultrastructure is tried to be revealed, but you can see that the gallium beam causes this large amount of curtaining. But if we would cut with an oxygen beam here, then much more of this ultrastructure can be revealed for the oxygen and ion beam. Another capability, really from a material science point of view, is rapid and convenient micromachining. So if you would have an area of 20 by 20 by 10 micron that you define, you can actually copy and paste that in a so-called array. So you can define the pitch in the X and the Y direction, and then you can basically just press the play button. And then after 5 minutes here, you have a relatively large volume milled and taking an image after that. With the SEM, you can really quickly define and create your own type of patterns. And you can create all kinds of shapes, not only rectangles. You can do circles, you can do lines, you can even do bitmaps as well. Okay, so I've talked mostly on the ion beam side of things. So let's go a little bit into the imaging detectors that we have available on this instrumentation. So we have a total of 6 detectors present. So the most standard or conventional one that's pretty much present in every SEM is the Everhard-Thornley detector that can be used in secondary electron mode. So you have a primary electron beam. This is the pole piece. You generate a variety of signals, and if you apply a positive bias to the detector, you can basically attract lower energy secondary electrons that are generated from your sample, and then visualize, for example, this cross-section in silicon, relatively large area cross-section, where we've deposited some tungsten on top of our region of interest to protect it from ion beam penetration. And then here we can see like more secondary electrons are generated on the tungsten, so that's why it's appearing brighter, and then the silicon appears more darker. So we can use that in backscatter mode as well. So now we would apply a negative grid bias to basically repel those secondary electrons. We can attract the backscatter electrons. So this is a backscatter image. Again, nothing really new for this type of detector, but we can also use it in ion beam induced secondary electron mode. So basically, when you are having your ion beam with any of the ions that I mentioned, xenon, oxygen, argon, nitrogen, that are impinging on your sample, you also generate these secondary electrons. When you apply a positive bias, then you can create a ion beam induced secondary electron image. The second detector is called the ion conversion and electron, or ICE detector. And so this is a very similar detector as the ETD, the Everhard-Thornley detector, but it's at a different location. It's actually near the ion beam. So when you basically apply a similar grid bias to it, you can, for example, in secondary electron mode, you attract lower energy secondary electrons, and then you can basically highlight different areas of your sample. I'll show another example of that shortly. This can also be used in secondary ion mode. So when you have your ion beam impinging on your sample, you also generate secondary ions. Those can be attracted if you apply a negative grid bias. Remember, we in the beginning we have had this soup of electrons and positively charged ions. So we can attract those to the detector and then simultaneously repel the secondary electrons to yield an image as shown over here from the cross section. So the IC the ICE detector can be complementary to the ETD detector, and you can actually acquire signals simultaneously as well. So an example or application of that is over here. The brighter area here in the ETD detector, there are more secondary electrons generated, and in the ICE detector, that is revealed more on this end. So, for example, if we look at this particle, that's much more highlighted over here versus in the ETD detector. That's as we would potentially describe in the shadow. So it's much more highlighted in this detector. And then if we look at our cross section again, there is more secondary electrons that are coming from this side wall, and in the ICE detector, that's basically the other side. So that this can be complementary. The third detector is a high resolution detector, also called a through the lens detector. So basically, we would submerge the sample in a magnetic immersion field, generally at very short working distances, and then basically the electrons can go into the pole piece. And again, if we apply that positive bias on our detector, we can drive the SEs into the high resolution detector. This is an example here on the right of a cross section of an alloy, where you can see first of all that you see a lot of these type of curtains, so we get more predominant surface information from our secondary electron signal here. This detector can be used in backscatter mode as well. So if we basically now apply a negative suction bias on the detector, you can repel secondary electrons, and then you can convert part of your backscattered electrons via this mirror into SE2s that can be attracted into the through the lens detector, and so you can basically get the backscatter image where now we have more chemical contrast, so higher average atomic number regions are showing up brighter. And what you can see also is that curtaining effect is much less visible in this image. The fourth detector is the in-column detector. So that's a detector that's basically the highest at the highest location up in the pole piece present, that really collects the most elastically scattered backscattered electrons and would give you the highest Z contrast image with the highest signal to noise images. So that's an example of that same region over here, and you can see here almost that curtaining is oh, we cannot see slides. Okay, everyone, can you see the slides? Okay, I was worried about that message. Sorry for the interruption. Okay, yeah, so if we compare, for example, the TLD with the ICD, so these can be acquired simultaneously as well. So here we can see the TLD detector that gives you really that surface topology in SE mode, with where there's no apparent Z contrast imaging, versus the ICD detector, which is a solid state detector. Sorry, I forgot to mention that. So it gives you really the highest Z contrast and highest signal to noise, and we barely see that curtaining effect present here. Right. The fifth detector is a retractable directional backscatter detector, so which can be used in an annular fashion. So you can select different areas of the detector with which you can detect different signals. Like if you select the inner ring, you get more of a Z contrast image, versus the outer rings, you can get more a topological type of image. And then we can also use it in a angular type of fashion. So if you would use different parts of the detector here, you can illuminate different parts of your sample, which, for example, could be used if you want to do like a qualitative 3D surface reconstruction or some sort of kind. We also have a retractable stem detector present here. So that can be used in various modes. We can have bright fields, so basically elucidate more mass contrast in this semiconductor sample versus high angular dark field mode, where we get more elemental contrast present. And so this detector can, for example, be beneficial if you're creating TEM lamella. You can, before you put it into TEM, albeit at lower accelerating voltage, you can kind of get an impression of how the quality of your sample looks like in the FIB-SEM. So we can also perform ultra high resolution imaging. So this is there are basically a couple of requirements in order to do so. And the first one is that you use the electron beam in a so-called monochromated mode. So there's a monochromator present in the Hydra SEM column that selects electrons with an energy spread less than 0.2 electron volts. You have to use this instrument at specific accelerating voltages and currents, though, for this to work. And then the second requirement is that you apply a technique called beam deceleration. So rather than just imaging the direct electron beam directly on the sample, you apply a bias on the stage. And so basically you get a different landing voltage. So you apply, for example, a 5 kV beam, you apply a 4 kV bias on the stage, you get a landing voltage of 1 kV, which gives you higher surface sensitivity and higher resolution signal. And then the third requirement is you need to be in that mode that I previously mentioned, the immersion modes in combination with the through the lens detector. And if you do that for a gold on carbon sample, then you can get a resolution of 5 angstrom. So yeah, the only SEM currently in our facility with a monochromator present. So the resolution is basically measured as a range in contrast between the edge of a gold nanoparticle and the carbon. Right, so I did mention we also have analytical detectors present. We have Oxford Instruments EDS detector, relatively large area present. So this is just an example of a cross-section of that metallic alloy where we have the higher Z contrast regions. This is about 50 nanometer region over here that we can see. And from the EDS mapping, we basically reveal that these grains are chromium inclusions in a nickel matrix, and then these small precipitates here appear to be niobium. So an example of such like a structure can be found over here. The niobium is shown in red here, and the chromium in blue. So we also have the Oxford Symmetry S3 EBSD detector present, which won the microscopy and microanalysis innovation awards this year. That was previously introduced by my colleague Tirza Abbott already. So this is now on the Hydra, the first instrument where it's installed and running, and so we can acquire high-speed data acquisition of the Kikuchi patterns now at about 5,800 patterns per second with this pixel resolution. And this is an example of that acquisition for a stainless steel sample where you can see different orientation grains highlighted, and about 85% in this at this high speed acquisition was correctly indexed. Okay, so we also have a micromanipulator present, but this is a relatively special one. If you compare it, for example, to the Helios, this one has rotation, and rotation allows you to do a lot of more things that we were previously able to do. So first of all, you could, for example, easily resharpen the micromanipulator. So you can trim it down on one end, you rotate 90 degrees, you trim it down on the other end, and you can basically sharpen it that way. You could lift out of large volumes, and now the rotation actually gives you precision to, for example, mount a sample onto a substrate, for example, for a TEM lamella onto a TEM half grid. But it also allows you to do much more flexible sample preparation, for example, for TEMs. So now that you have rotation, so rather than a top-down approach where you usually would lift out a cross-section of your material, you thin it down and look at it in a TEM, you could basically invert that cross-section. So there's a series of steps that you would need to take. For example, if you would rotate the micromanipulator 180 degrees, that results in a rotation of your sample of 90 degrees. So you can basically lift it out, rotate it, attach it, cut it free, then rotate the sample stage 180 degrees, you lift it out again, rotate it back again, and then mount it on a FIB grid. And now you can basically mill your sample upside down. So to give a little bit more insight, I just put this schematic over here, the conventional top-down method, basically, where you have like embedded features that you would analyze in the TEM. Now you can, with the rotation, you have much more flexibility. You can rotate your sample upside down. You can create inverted lamellas or plan view lamellas. If you have buried multi-layer structures, you can rotate that and then thin it down, the sample down. So much more flexible TEM sample preparation. Right. So besides this wealth of hardware, we also have various type of softwares present that work in hand with the hardware. So we have AutoTM5, which is an automated software with which you can prepare TEM samples, not in a fully automated way, but in a nearly fully automated way. The lift out is what we still call like a guided approach. So you have some pictures where you can say like, oh, I would like to move my lamella here and here. Then we also have auto slice and view. So that's that software for so-called serial sectioning. So that's basically to create 3D imaging of your volume. But this also has integrated 3D EDS and 3D EBSD capabilities. The third software that I'm going to discuss in more detail is MAPS3. That's basically a correlative type of a platform where you can, for example, correlate optical image data with electron microscopy data together. And then the fourth one is Avisu 3D, which is software for image data visualization and analysis. Right, so let's start with the AutoTM5. So on the left-hand side, if you would go to the Thermo Fisher Scientific website, you can see this, beautiful image of various areas with where TEM samples with nanometer scale precision have been prepared. So basically, it's an optimized recipe for one area, and if you copy and paste that recipe multiple times, then you can basically in the software just let it run, and after ideally after a couple of hours you come back, you do something in the meantime, and then you at the end you would have an amount of samples, in this case maybe 12, that would be automatically prepared. Now that seems to work, of course, fine for things like silicon. So silicon is like the perfect material to mill. So I attempted to do this on a material that was much more coarse and a little bit more intricate to prepare. So in this case, I had a electrical sensor. This is actually a bioresorbable nerve stimulator with multi layer metals that are present: copper, gold, titanium on a molybdenum substrate. And so I optimized the recipe for one area and made sure that the section looked good. Then I basically let the program run, and indeed I was able to create 12 TM lamella in 7 hours in an automated fashion. And then I dove in with the ICD detector and then just analyzed the cross section to see what the variability of the thickness of these metal layers were. So just showing you this video one more time for the 12 cross sections. So I think 11 of these were a success, and number 12 was a little bit strange, but nonetheless, quite impressed with this initial testing. Right, then the auto slice and view software, which is basically a software for again the 3D imaging or 3D analytical EDS EBSD data. So what happens in this approach is basically you create a region, so you carve out a region with the ion beam, you remove a small slice of material with the ion beam, and then after you expose it to electrons, and then you can collect various signals to create an image of your cross section. And if you repeat that multiple times and you can layer them together, you can create a 3D visualization of the volume that you removed. So this is just a screenshot of that software. So what we see over here is basically an ion beam image. So we're at a stage tilt of 52 degrees to turn perpendicular to the ion beam. And down here in the software is like a workflow. So you can have a workflow where you have so-called area preparation. So you can remove areas surrounding your material so that it's visible to the electron beam. And then you have, for example, a milling step. And if you click on one of these steps, then you get other parameters that you can tune. And there is a whole variety of parameters that you can select. Part of the area preparations, for example, also this fiducial, so that every time that the ion beam slices, there is a drift correction performed first, that there is a matching score, and then it removes a layer of material exactly in the right place. On the right-hand side here, this is, for example, the SEM imaging tab. So this is an electron beam image. By the way, this area is about like 75 microns or so wide, so it's a relatively large cross-section. And there, again, you have a multitude of parameters that you can set. You can set things like you have different autofocus or auto-stigmation strategies that you can apply. Do you fast focus or slow focus? You can use multiple detectors simultaneously, like I highlighted before, for example, the TLD and the ICD detector simultaneously for backscatter comparison. Then there's other things available in the software as well. For example, you can do a rocking polish. So a rocking polish is basically if you, after you remove a focus, a slice of material, for example, you see that the cross section is not good, there's a lot of curtaining, then you can decide, okay, I want to build in a rocking step. So you tilt the sample at a specific angle and rotate it so that the ion beam impinges on your sample in a different direction. And if you do that back and forth, so basically it's rocking back and forth, that's where the name rocking comes from, then you can minimize artifacts such as curtaining. I think we can improve a bit here, but the right-hand image is with that rocking step. So you can build this in after every slice or after every 10 slices, 20 slices. It's very flexible in that manner. This is just an example of multimodal acquisition. So where you have like 3D EDS data and 3D EBSD data. This is not work that was performed here, but just to give you an idea, these are precipitates in an alloy again. And so not only can you elucidate where the chemical composition of these of the alloy is here, but you can also get crystallographic information with the EBSD, for example, looking where grain boundaries near these precipitates are. And so you have this multimodal acquisition that's possible. Then the correlative software on the left-hand side, again, is a screenshot of the interface. Here we have just the sample stage in the microscope. So by the way, we can load up to 21 SEM stubs on our stage. So basically you can correlate an optical image, and then you can create electron microscopy data at high resolution, high pixel density, etc. So many hundreds of images that the software can stitch automatically together, again with various focus strategies built in, etc. So I can compare this kind of like to some of you are probably familiar with Google Earth, where you have a country and you can zoom in, and you can pretty much zoom in like endlessly, and you start with a country and you end with somebody's car, for example. On the right-hand side, we have stitched STEM images of nearly an entire TEM grid, so about a 3 millimeter grid that have been stitched together. So you can use this for a variety of detectors as well. Okay, then coming to the visualization software, the Aviso 3D. So let's assume we've created a 3D image stack where we have some particles into a matrix. Then we would segment, if we're interested, for example, in the particles, for example, to look at areas or volumes, then we can segment this data. And for example, if we would assign values to it, the matrix is 1, and then the particles is 2. And then we can perform some analysis where we can get things like volume. So the color coding here matches to a specific volumes. So that can be done in the Aviso 3D software. And this is, again, a screenshot of the interface where we have a specific workflow. So you can do image manipulation, you can do filtering, etc. So there's usually many steps that you can include. Then, so these are course steps, and then every step, if you would select it, you get a submenu where you can define and tune specific parameters. And then on the right-hand side here, you can use this for visualization. In this case, we have like again a cell that's where we can visualize the ultrastructure of. Right. So basically, we have now discussed pretty much all material science examples. And I would just like to dive into like the prospects of this instrument when we would consider cryogenic conditions. So again, if you look at the length scale that we could achieve with a FIB-SEM, again, it's that sub-millimeter range that I said up until the nanoscale. So with the cryo FIB-SEM, we can do the slice and view, so the 3D tomography at cryogenic conditions. But we can also do cryo lift out of samples, so we can prepare TEM samples at cryogenic conditions. So we have a micromanipulator and a cryo stage that can operate at cryogenic conditions. Now, the current feature that we don't have yet present, but we hope to get, and I'm very interested in and keen to get it here. So if you're interested in that capability, then we can please approach me, that we can figure out potential further strategies to get this here. Is the presence of a cryotransfer shuttle. So when you have biological tissues, you can preserve them in their native state via vitrification or high pressure freezing. But currently, we would need a transfer shuttle to transfer that to the cryo FIB-SEM. Then you can perform, for example, the 3D tomography of these structures in their native environment. But also that would allow for transfer, cryo transfer to various instrumentations such as TEM. So if we would want to access these biological structures basically at atomic resolution, so basically expand the length so that we can characterize these materials with, then we can perform cryo-TM or cryo-electron tomography in order to visualize the near atomic structure. And this is just a nice work that was recently published in Nature Methods by the Max Planck Institute, Jürgen Plisko and co-authors, that basically performed vitrification of an entire organism. Then using the PFIB, they sliced this into larger slices, then thin down the slices individually. So here you can see that process. So basically the blue is the vitreous ice, and then the organism, they cut this into small slices along. This is a FIB tomography grid. So that here in the SEM and the TEM, you can see these various slices. And then they performed electron tomography and they recreated the whole organism. But now they have access, again, like that Google Earth example, they can really dive in and now visualize. In this case, it's a ribosome at 6.9 angstrom, I believe, resolution. So they can really dive and analyze this complete organism. So yeah, I think with that, I would like to pretty much end the technical talk. So if you're interested in accessing the Thermo Fisher Plasma FIB-SEM, currently we're training users that have FIB-SEM experience, and there is currently a waiting list. So I ask you for your patience, but if you would like access, please contact me. And then we can coordinate henceforth. Last but not least, I'm very excited to introduce Dr. Yu Wen that joined our EPIC team since last week and will help out with FIB and TEM related facility efforts. So if you meet her, give her a warm welcome. And then I would like to, thank you all for your attention. I end with this image of the PFIB chamber, and I would be happy to take any questions. Thank you.